What if the biggest mistake in modern science is not about black holes or dark matter, but about how fast the universe is expanding? For nearly a century, astronomers believed they had measured the expansion of the cosmos with extraordinary precision. But today, the two most accurate measurements ever made disagree so strongly that they cannot both be right. Method looks at nearby galaxies and says the universe is expanding at one speed. The other looks back almost 13.8 billion years to the faint afterglow of the Big Bang itself and predicts a completely different answer. Both methods have been tested, refined, and confirmed by the most advanced telescopes humanity has ever built, and yet the numbers refuse to match. At first, scientists blamed faulty instruments. Then they blamed dust, calibration errors, and flawed observation. But as the James Webb Space Telescope and the Euclid mission delivered even more precise data, the mystery only became deeper. Instead of solving the problem, they uncovered ancient galaxies and supermassive black holes that should not have had enough time to exist. So what if the universe is not expanding the way our best theory predicts? What if the problem is not our telescope but the model we have trusted for decades? Because if the Hubble tension is real, it could mean that the biggest discovery in cosmology is not behind us. It is happening right now. The number at the center of this fight is called the Hubble constant. In plain language, it tells you how fast space stretches today. Measure it in kilometers per second for every megaparsec of distance, and you get a rate. Farther galaxies recede faster in proportion. That single number does more than describe motion. Combined with the rest of a cosmological model, it helps set the age of the universe, the scale of cosmic distances, and the timeline available for galaxies and black holes to grow. Get the expansion wrong, and every clock built from that expansion drifts. Imagine standing on a stretch of highway where every car farther ahead seems to pull away faster. The pattern is not about the cars themselves racing through empty space, the way a rocket leaves Earth. It is about the road lengthening between them. Cosmology's version of that road is space-time. The Hubble constant is the present stretch rate of that road. Change the rate, and the travel time since the Big Bang changes. Change the travel time, and every story about how soon a galaxy could assemble or how soon a black hole could fatten has to be rewritten. Megaparsec is roughly 3.26 million light-years, a distance so large that light itself needs millions of years to cross it. Saying the expansion is 73 kilometers per second per megaparsec means that for every megaparsec of separation, recession speed jumps by 73 kilometers each second. 9% of that rate is not a rounding error in a school notebook. It is a missing chapter. 7 sigma is not a coin flip bad day. It is the kind of statistical distance that would make a particle physicist announce a discovery if the signal were a new particle. Here the signal is a mismatch. For decades, the hope was that better telescopes would make the Hubble constant converge. Measure carefully enough, and two independent methods should meet. Instead, the opposite happened. As the error bars shrank, the disagreement grew. That is the hallmark of a real tension, rather than a noisy measurement. Noise fades with better data. Wrong assumption becomes louder. Start with the method that looks nearby, the cosmic distance ladder. Imagine climbing a ladder where each rung calibrates the next. The first rungs are geometric. Parallax uses Earth's orbit around the Sun to measure tiny shifts in nearby stars. Those nearby distances train the next class of objects, standard candles, sources whose true brightness can be inferred, so their apparent dimness reveals distance. The historical foundation of those candles is Henrietta Swan Libet's work in 1908 at Harvard Observatory, cataloging variable stars. She found that Cepheid variables with longer pulse periods are intrinsically brighter. Measure the period, infer the true luminosity, compare with the observed brightness, and distance follows. That period luminosity relation became astronomy's first reliable cosmic tape measure. High does a Cepheid pulse at all. Inside these yellow giant stars, a layer of partially ionized helium acts like a valve. When the star expands and cools, the layer becomes more transparent and heat escapes. When it contracts and heats, opacity rises and radiation is trapped, pushing the star outward again. The result is a stable oscillation. Longer period sephides are larger and more luminous. Leavitt did not know the full interior physics in 1908. She knew something more dangerous for dogma, a clean empirical rule that turned blinking points of light into distances. Modern space missions like Gaia refined the geometric first rungs with catalogs of stellar positions, so precise that the base of the ladder stopped wobbling the way it did when astronomers had only ground-based parallaxes. Without a solid geometric base, every later rung inherits a systematic lean. If your 0 point is wrong by 1%, your Hubble constant is wrong by 1%, and 1% is exactly the battlefield where 73 fights 67. Vesto Slipher then measured the Doppler shifts of spiral nebulae and found most racing away. Edwin Hubble, using Cephides and Andromeda and other systems, proved those nebulae were galaxies beyond the Milky Way. In 1929, he published The Relation Between Distance and Recession Velocity. The universe expands. His first value for the expansion rate was catastrophically high, around 500 kilometers per second per megaparsec, implying a cosmos younger than Earth. The discovery was right, the calibration was wrong. Between 1916 and 1927, Einstein applied general relativity to the cosmos and preferred a static universe, inserting a cosmological constant to hold the geometry still. William de Sitter, Alexander Friedman, and George Lemaitre explored expanding solutions anyway. Lemaitre even connected recession velocities to an expanding space. Before Hubble's famous plot made the idea public property, the mathematics was ready, the culture still wanted stillness. Then the data chose motion. When Harlow Shapley received Hubble's letter, proving Andromeda lay far beyond the Milky Way, astronomy law kept the line. Here is the letter that destroyed my universe. Corrections came in waves. Walter Baade showed Hubble had mixed different kinds of Cephides. Alan Sandage found that many of Hubble's supposed bright stars were star clusters or glowing gas. The expansion rate fell toward modern ranges. From the 1970s through the 1990s, astronomy fought what people later called the second Hubble tension. Sandage arguing near 50, others near 100. Robert Kirshner later joked that disagreeing by a factor of 2 is like not knowing whether you have 1 foot or 2, while arguing over 10% is like fighting about a toe. Precision had entered the room, so had disagreement. The Hubble Space Telescope was launched partly to settle that fight. Wendy Friedman's key project delivered a result near 72, with still large uncertainties. For a time, the field felt the number was converging. Then another discovery rearranged everything. In 1998, distant Type Ia supernovas appeared too faint for their expected distances. Adam Rees, Brian Schmidt, Saul Perlmutter, and their teams concluded the expansion was accelerating dark energy. The cosmological constant Einstein once regretted returned as the dominant ingredient of the late universe. Rees, Schmidt, and Perlmutter shared the Nobel Prize in Physics in 2011. Lambda CDM became the standard model of cosmology, cold dark matter plus dark energy on Einstein's expanding geometry. Dark energy, amounting to roughly 70% of the present energy budget, turned Einstein's discarded cosmological constant into the dominant ingredient of the late universe. Lambda CDM then had to explain everything else with only about 6 free parameters: the microwave sky, light element abundances, large-scale structure, and acceleration. That success is why a 9% Hubble mismatch feels like betrayal rather than weather. Lambda CDM is extraordinarily successful. With a handful of parameters, it explains the pattern of the cosmic microwave background, the abundance of light elements, the growth of large-scale structure, and the accelerated expansion. That success is why the next disagreement hurts. The model is not a casual guess, it is the map that works almost everywhere. Big Bang nuclear synthesis is one of those quiet successes people forget when headlines scream crisis. In the first minutes after the Big Bang, the universe cooked a predictable mix of hydrogen, helium, and traces of lithium. The observed abundances still match that kitchen recipe under Lambda CDM assumptions about ordinary matter. Any new early ingredient invented to fix the Hubble constant must not burn that kitchen down. That constraint is why early dark energy has to be brief, carefully timed, and then gone. A guest that leaves before dinner is ruined. The second method for the Hubble constant does not climb the local ladder. It starts at the beginning, when the universe was about 380,000 years old. Electrons and protons combined into neutral atoms and light streamed freely for the first time. That light, stretched by expansion into microwaves, is the cosmic microwave background, the afterglow of the Big Bang. Satellites like Planck map tiny temperature variations across that ancient sky. Those variations encode the size of sound waves that traveled through the hot plasma before atoms formed. That scale is called the sound horizon. Picture the early universe as a fog of charged particles and photons locked together. Gravity pulled denser regions inward. Radiation pressure pushed them outward. The plasma rang like a cosmic drum. When atoms formed and the fog cleared, those frozen sound patterns became the hot and cold spots. Planck photographed the angular size of the first acoustic peak is one of the cleanest numbers in science. Turning that angle into a present-day Hubble constant is where the model enters. You need the expansion history between then and now. Lambda CDM supplies that history. If lambda CDM is incomplete, the translation from infant sky to today's stretch rate is where the error hides. There is a cousin of the same early ruler still visible in the late universe: baryon acoustic oscillations. The sound horizon also left a preferred separation scale in the clustering of galaxies. A faint frozen ripple you can still measure in large surveys. That BAO scale, combined with Big Bang nucleosynthesis constraints on ordinary matter, offers another route to today's expansion under the standard model. In 2026, the local distance network's clash was not only against Planck plus lambda CDM, it was also quoted at about 5 sigma against BBN plus BAOO combination. The early universe keeps voting low. The local universe keeps voting high. If you know the sound horizon's physical size from physics, and you measure its angular size on the sky, you can infer distances and expansion history. But only by assuming a model that connects the early universe to today. Under lambda CDM, Planck's map predicts a present expansion rate near 67 km per second per megaparsec. Local ladder measurements, especially the SHOES program led by Adam Rees, keep finding values near 73. The gap is about 9 or 10%. With modern uncertainties, that discrepancy has climbed past 5 standard deviations and, in recent combined local analyses, beyond 7. In particle physics, 5 sigma is discovery territory. Cosmology is staring at a disagreement, that size between a prediction and a measurement. Watch how the Third Hubble War escalated, because the escalation is the plot. In 2013, Planck's early maps gave about 67.3 with larger uncertainty, tension of only about 2 or 3 sigma. By 2016, SHOES reported about 73.2. Planck's 2018 release tightened the early prediction and pushed the clash toward 5 sigma. SHOES updates kept landing near 73. Friedman's tip of the red giant work around 2019 sat near 69.8. An intermediate camp that kept the argument honest. Zero Lico around 2021 found about 73.3. Keck time delay work in late 2025 again landed near 73. Then, the local distance network in 2026 reported about 73.5 with roughly 1% precision, tension above 7 sigma. Every decade of better data made the mismatch louder. Hold the difference carefully. The local method measures today's expansion more directly. The early universe method predicts today's expansion through lambda CDM. If instruments on both sides are clean, the model is the suspect. That is why Stefano Casatano could say the prevailing cosmological model predicts a Hubble constant about 10% smaller than what we measure directly. That is why Adam Rees argues that confirming the tension makes it more important to re-examine the foundations of the current model. That is why John O'Meara of Keck Observatory warned that cosmology, as we know it, may be broken if the tension is not a measurement error. And that is why Tommaso Troy called this the possible beginning of a new cosmological model. Scientists did what good scientists do first. They tried to kill the tension with systematic. Dust can redden stars and bias brightness. Metallicity can change Cepheid behavior. Crowding can blend stars in dense images. Calibration of the ladder's first rungs can shift every later step. Type Ia supernovas may evolve with cosmic time. On the CMB side, details of recombination physics, neutrino assumptions, and analysis choices can move the inferred rate year after year. Teams hunted these ghosts. Some corrections mattered, none erased the gap. Near-infrared Cepheid work matters for a reason you can picture. Dust in a host galaxy acts like a dirty window. Optical light suffers more. Infrared light punches through. If local distances were artificially large because dusty windows made stars look too faint, infrared should pull those distances back and lower the Hubble constant toward Planck. In several Schu's analyses, the infrared path did not hand the victory to the early universe. It reinforced the high local number. That single fact killed a favorite villain. The Schu's program's obsession is almost a character in this story. After helping discover acceleration, Adam Rees turned the local Hubble constant into a precision campaign. Cepheids in supernova hosts, near-infrared observations to fight dust, Gaia anchors, repeated cross-checks. Critics sometimes paint that focus as stubbornness. Supporters call it the only honest response to a 5 sigma wound. Either way, someone kept measuring until the error bars had nowhere left to hide. Peculiar motions. The sideways traffic of galaxies falling into clusters are why you cannot measure the Hubble constant with only the local group. You need distance, you need recession, you need a stretch of cosmic highway long enough for expansion to drown the local weather. That highway is what the ladder buys when it reaches Type Ia supernovas in the Hubble flow. Independent rungs were built to cross-check Cepheids. The tip of the red giant branch, TRGB, uses the sharp luminosity cutoff of aging red giants. Mira variables offer long-period alternative megamasas in water disks. Give geometric distances. Iron delay cosmography uses gravitationally lensed quasars. Multiple images arrive at different times, and the delays encode distances. Surface brightness fluctuations, Tully Fisher, and the fundamental plane add more roots. When methods that share few assumptions still lean high compared with Planck under lambda CDM, the tension looks less like one broken tool. The tip of the red giant branch deserves its own sentence of awe. When low-mass stars exhaust core hydrogen and climb that branch, electron degeneracy in the helium core triggers a helium flash at a nearly universal brightness in old population. That cliff in the color magnitude diagram is a distance marker that does not require a Cepheid's pulse. Mira variables, with periods of hundreds of days, add another long period path. When methods that share few assumptions still lean high compared with Planck under lambda CDM, the tension looks less like one broken tool. Type Ia supernovas deserve a closer look because they'll carry the laid ladder. White dwarf in a binary can steal mass from a companion until carbon ignition runs away. The explosion is not identical every time, but after corrections for light curve shape and color, the peak becomes a standardizable candle bright enough to be seen across a large fraction of the observable universe. Megamasas in water disks skip candle assumptions entirely. Radio astronomy watching a spinning disk of water vapor lasers and reading Keplerian motion directly into distance. Time delay cosmography is almost a different science. Foreground galaxy bends light from a background quasar into several paths. Because the paths have different lengths and different gravitational time delays, the flicker of the quasar's engine arrives staggered. Measure the stagger, model the lens mass, and cosmology falls out. Projects such as H0 LICO W and later Keck campaigns used that trick to land near the high local values. An almost entirely independent vote from Cepheids. James Webb entered this fight as a possible referee. Its larger mirror and infrared vision resolved stars in galaxies where Hubble saw blends, and they pierced dust that once scrambled calibrations. Some expected Webb to reveal that local distances were overestimated, pulling the local Hubble constant down toward Planck. Wendy Friedman's Chicago Carnegie Hubble program, combining Hubble and Webb data, reported in 2025 a value near 70.4 with roughly 3% uncertainty, closer to the early universe prediction, and accompanied by Friedman's claim that the standard model was holding for the Hubble constant at that moment. The Schu's team, and later local distance network analysis, continued to find values near 73 with about 1% precision. In early 2026, the Local Distance Network compilation reported about 73.5, with tension against lambda CDM plus CMB quoted above 7 sigma, and strong tension also against combinations using Big Bang nuclear synthesis and baryon acoustic oscillations. Webb is often described as roughly 4 times sharper in resolution class than Hubble, and an order of magnitude more sensitive for the faint infrared work this fight needs. A mirror about 6.5 meters against Hubble's roughly 2.4. Some expected those better eyes to end the argument cleanly. Overestimated local distances, tension collapses, model saved. So even among local observers, the debate is not finished. Different treatments of the same kinds of stars can still move the answer. But notice what did not happen. Webb did not make the problem trivially disappear into dust. In several analyses, infrared data strengthened confidence in Cepheid distances rather than destroying them. Time delay cosmography from facilities including Keck continue to land near the high local value. The tension is no longer a story of one noisy ladder against one satellite. It is a stubborn mismatch that survives new instruments. Hold Friedman and Rees in the same frame without turning them into cartoon rivals. Both spent careers making the ladder sharper. Both use space telescopes the public trusts. Both publish numbers with error bars that used to be science fiction. No analysis lands nearer 70. Noplin's nearer 73. The public story should hold both facts. The tension between early and late cosmology is historically severe, and the local community is not unanimous on every decimal. Honesty strengthens the mystery rather than watering it down. While the expansion rate argued with itself, Webb and Euclid made the cosmic timeline feel shorter from another direction. Early galaxies appeared brighter, more massive, and more structured than many pre-launch forecasts. Some of those monsters were later partly explained by active black holes inflating brightness. The little red dots that fooled stellar mass estimate. Even after corrections, surveys still found more early massive systems than many lambda CDM-based expectation. In 2025, Webb reported giant spiral structure, the so-called Big Wheel, within the first roughly 2 billion years, when many expected chaotic ellipticals rather than orderly arms. Growth in place, without endless violent mergers, may be more important than textbooks emphasized. 2 kinds of early galaxy anomalies stacked after Webb's first deep looks. Extreme ultraviolet brightness in the first roughly 400 million years, and an excess of massive systems across the first roughly 2 billion years. Compared with many simulations, partial fixes arrived when active black holes, the little red dots, inflated brightness and fooled stellar mass estimates. NASA's messaging eventually said, early galaxies were not always too big for their britches. Even after corrections, residual excesses remain. In 2025, the so-called Big Wheel showed giant spiral arms within the first roughly 2 billion years, when many expected chaotic ellipticals. Growth in place, without endless violent mergers, may matter more than textbooks emphasized. Euclid, launched in 2023, with a field of view hundreds of times. Hubble's swept thousands of square degrees. By mid-2026, it reported 31 primordial quasars, including systems when the universe was only about 670 million years old, roughly 5% of its present age. Central black holes around 100 million solar masses, grown by huge factors in only a couple of 100 million years, with host galaxies forming hundreds of solar masses of stars per year, and black hole-to-galaxy ratios suggesting holes that outpace their hosts. Seeds of at least 1,000 solar masses are discussed because ordinary stellar remnants struggle to feast fast enough. Euclid had covered only a fraction of its planned area. More are coming. In its first roughly 18 months, Euclid covered about 3,000 square degrees, around 1/10 of the sky, with a field of view about 270 times Hubble's. Daming Yang at Leiden University used machine learning to pull quasar candidates from millions of sources. Follow-up spectroscopy came from Keck, Magellan-Bardet, and the Large Binocular Telescope. The shock was not only that the quasars existed, It was that many were typical, not freak outliers, a population, not a lottery ticket. Central black holes around 100 million solar masses grew by factors of about 100 in only a couple of 100 million years. One Euclid host forms stars at roughly 250 solar masses per year. Black hole-to galaxy mass ratios near 100 to 1, compared with roughly 200 to 1 locally, suggest holes that outpace their hosts. The Eddington limit is the speed bump. Eat too greedily and radiation pressure pushes fuel away. Growing monsters this fast demands near-continuous feasting or heavy seeds of at least 1,000 solar masses. Euclid had covered only about a quarter of its planned area. More are coming. Why do these discoveries belong in a Hubble tension story? Because expansion history sets the available time if the universe is younger than the concordance picture assumed, or if growth was faster for reasons the model misses. Early monsters and a high local Hubble constant become chapters of one incomplete map. They are not identical problems. Wrong distance ladder does not automatically create quasars, but both ask whether lambda CDM's bridge from the early universe to today is missing. Physics. Early dark energy was proposed precisely because it might touch both. Early dark energy is a temporary anti-gravitational component that would have acted briefly in the young universe, thousands of years after the Big Bang in typical models, then faded away by speeding expansion before atoms formed. It shrinks the sound horizon. Smaller physical sound horizon, seen at the same angular size in the CMB, changes the inferred distances and allows the model to predict a higher present Hubble constant closer to local measurements. That is the Hubble fix. Think of the sound horizon as a frozen yardstick printed into the microwave sky. If that yardstick was physically shorter than lambda CDM assumes, then matching the same angular size on the sky means the inferred distances change, and today's predicted stretch rate rises. Early dark energy shrinks the yardstick without throwing away Planck's photograph. The photograph stayed. The caption changes. Poulin and collaborators proposed versions of this around 2019 in a paper that gathered well over 1,000 citations, with Mark Kamienkovsky among the prominent advocates. In 2024, work associated with Shuejian Shen, Rohan Naidu, Michael Boylan-Kolkin, Mark Vogelsberger, and collaborators argued that early dark energy can also help early galaxy formation by altering the expansion and growth history in ways that make massive systems appear sooner. Naidu called it an elegant, lean solution to two urgent problems. Boylan-Kolchin noted that explaining two unrelated crises makes the idea worth pursuing hard as web data deepen. The idea itself goes back to papers such as Poulin and collaborators around 2019, with Mark Kamienkovsky among the prominent advocates of early universe modifications. But elegant is not proven. Early dark energy must face the full data set: CMB peaks, large-scale structure, lensing, and late-time expansion. Some versions help the Hubble constant while stressing other observables: ultralight axions, stellar neutrinos coupled to new fields, dark radiation interacting with a dark matter subcomponent, and dissipative early dark energy variants have all been tried to reduce the tension. Late-time fixers, evolving dark energy, modified gravity, face their own no-go pressures from distance duality and inverse distance ladders. Purely local explanations, such as living in a giant underdense void, have been largely discarded as a full solution. 2026 review by Kai and Wang emphasized that isolated early-only or late-only patches struggle, and that remaining viable options favor combined early-late modifications or new physics at the transition between inhomogeneous and homogeneous regimes. Ultralight axion-like particles can shift early expansion enough in some models to reduce the tension toward roughly 2 sigma without solving everything. Variants couple rotating axion fields to baryogenesis or to gauge interactions that create thermal friction. Dissipative early dark energy cousins that try to ease both the Hubble clash and related growth tensions, sometimes discussed under an S8 mismatch in how strongly matter clusters. Sterile neutrinos weakly coupled to new scalar fields have been floated. Dark radiation interacting with a dark matter subcomponent has been tried and constrained. Late-time suspects include modified gravity of the F of R family, squeezed by large-scale structure, and dynamical dark energy that evolves instead of staying a pure cosmological constant. An evolving dark sector rearranges late expansion without touching the sound horizon. A different crime scene, purely local voids that trick the latter have been largely discarded. The void would have to be enormous and carefully tuned. The sky does not cooperate. There is another way to feel the early ruler without climbing SEP heights. The inverse distance ladder. Start from the sound horizon, use baryon acoustic oscillations as a standard ruler through cosmic time, and walk forward until you predict today's Hubble constant. That path still lands near the low camp under lambda CDM. Distance duality is the quiet bouncer. Luminosity distance and angular diameter distance stay locked in standard geometry. Many exotic late-time tricks try to break that lock and fail the checklist. That is what Kai and Wang's no-go pressure means in practice. Wendy Friedman has noted that more than 1,000 papers have attacked the problem, and it has been extraordinarily difficult. That mountain of theory is itself a clue. Easy systematics would not spawn a literature that large. Simon Birra called the situation every physicist's dream. Find something wrong in our understanding so we can discover something new and deep. The dream and the nightmare are the same fact. A crack in the most successful cosmological model ever built. Think of lambda CDM as a city map that works for 99% of streets. Then you find a neighborhood where the map says north and the road runs south. Is the map wrong? Or did you miss a one-way rule that changes direction? The Hubble tension is that neighborhood. Webb's early galaxies and Euclid's quasars are additional blocks that refuse the old tourist brochure. Maybe they share one cause, maybe they are separate. Either way, the map needs a revision note in ink, not a shrug. There is a historical rhyme. At the end of the 19th century, classical physics predicted that a hot object should radiate infinite ultraviolet energy. The ultraviolet catastrophe. The contradiction was intolerable. Max Planck's quantization did not merely patch a formula, it opened quantum mechanics. Persistent, precise anomalies are how revolutions announce themselves. Nobody can yet promise that the Hubble tension is that kind of anomaly, but its statistical strength and its refusal to die under better telescopes are why serious people use the word crisis without embarrassment. Return to the two speeds in human terms. Look at nearby galaxies with Cepheids and supernovas, and space seems to stretch faster. Look at the infant universe's afterglow and ask lambda CDM what today should be. And space seems to stretch slower. Both answers are precise. Both are built by communities that have spent careers hunting their own mistakes. The universe is not obligated to make those answers match. Our theory is, lambda CDM is cosmology's standard model, the way the particle standard model is physics. Powerful, incomplete, and dangerous to discard casually. The particle model does not explain dark matter, dark energy, or neutrino massive. Cosmology's model does not automatically explain a 9% mismatch at 7 sigma. Incompleteness is not failure. Pretending the gap is not there would be. Notice how personal the stakes feel for a science that usually hides behind equations. If the model is incomplete, textbooks rewrite the fate of the universe. The long-term stretch, the growth of structure, maybe even the identity of the dark sector. If the model holds and the ladder still hides a flaw, then a generation of distance work must be rebuilt from the first rung up. Either path is historic. That is why O'Mara can say cosmology may be broken, why Troy can smell a new model, why Friedman can still defend the standard picture, and why none of them is performing. They are describing different bets on the same table. If the local rate is right and the model is incomplete, the universe may be younger than the classic 13.8 billion year story implied under older assumptions, or the expansion history may have taken a shape lambda CDM never allowed. G is not a single lever. It depends on the whole history of expansion. That is why headlines that simply subtract a percentage from the age are too crude. The real implication is sharper. The bridge from recombination to now may contain unknown physics, and that unknown physics rearranges clocks, distances, and growth. If early dark energy existed, it would mean dark energy is not only a late-time mystery. Something dark and dynamical may have spoken once in the first moments after the Big Bang, vanished, and left a fingerprint in every distance we infer from the CMB. That would unify two dark puzzles into one family. Dangerous intellectually, because it multiplies unknowns, and powerful if the data demand it. If dynamical late dark energy is instead the culprit, the night sky's acceleration is not a fixed cosmological constant, but a process still evolving. A living dark sector rather than a frozen lambda. Reionization adds another clock to the same desk. After recombination, the cosmic dark ages lasted until the first stars and black holes flooded space with ultraviolet light. Webb's luminous early systems and Euclid's early quasars are candidate floodlights. If they appear too soon, they stress ionization history as well as galaxy recipes. Expansion rate, structure growth, and reionization are three dials on one machine. What if both Hubble numbers are somehow wrong in compensating ways? Philosophers love that escape hatch. Working cosmologists hate it because it demands two independent conspiracies with the same magnitude and opposite sign. The cleaner hypotheses are the ones the field actually funds, remaining systematic at the percent level, or new physics that changes the bridge from the sound horizon to today. If the tension somehow collapses under a future calibration revolution, science still wins. Webb, Euclid, Gaia parallaxes, better supernova physics, and cleaner lens time delays would have stress-tested the distance ladder at a level no previous generation could. Solved tension is still a triumph of method, and unsolved tension is a door. Either outcome beats polite agreement that hid an error. Reionization adds texture to the same calendar. After atoms formed at recombination, the universe went dark for a time, until the first stars and black holes flooded space with ultraviolet light and ionized hydrogen again. Webb's luminous early systems and Euclid's early quasars are candidate floodlights for that era. If they appear too soon and too bright, they stress not only galaxy formation recipes, but the ionization history simulations thought they understood. Expansion rate, structure growth, and reionization are three dials on one machine, and the Hubble tension may be the finger turning more than one. Some cosmologists also watch a related growth tension often discussed under the name S8, a parameter describing how strongly matter clusters on certain scales. Early dark energy variants with thermal friction have been marketed as possible dual remedies for the Hubble clash and clustering mismatches. Whether those dual remedies survive the next round of weak lensing and galaxy clustering surveys is an open courtroom. The cracks in lambda CDM may not be isolated, they may be a pattern. Watch how the argument feels from inside a research team. You measure a Cepheid period in a galaxy that also hosted a Type Ia supernova. You convert period to luminosity with a calibrated relation. You convert supernova brightness into distance. You assemble dozens of such distances and plot velocity against distance. The slope is the Hubble constant. On the other side of the world, a team fits thousands of CMB modes with a Boltzmann code under lambda CDM and reads off a predicted slope. Two slopes near cosmos. The disagreement is not abstract philosophy. It is two numbers on two screens that refuse to become one. Now add Webb's early galaxies to that screen. Hierarchical formation said small systems first, giants later. The telescope found luminous, structured, sometimes already quenched systems shockingly early. Partial fixes exist: active nuclei, bursty star formation, top-heavy stellar population. Residual excesses remain. Euclid's typical early quasars, say black hole seeds and feeding, were efficient when the universe was a few percent of its current age. Time as the currency both crises spend. Expansion history mints that currency. So when the opening asks whether the universe is expanding wrong, it does not mean galaxies are flying through space like shrapnel from a bomb. It means our best bookkeeping of the stretch rate does not close. Something in the measurement chain or something in the physical model is missing after years of blaming dust and instruments. The missing page looks more and more like physics. Lambda CDM will not be discarded lightly. It still explains too much. The path forward is not a bonfire. It is a set of decisive tests, larger samples of lensed quasars, cleaner Cepheid and red giant calibrations with Webb, cross-checks that avoid shared rungs, MB measurements with new experiments that test Planck's assumptions, large-scale structure surveys that constrain early dark energy's fingerprints, galaxy and quasar counts at high redshift that demand a growth history consistent with whatever expansion history solves. H0. Kai and Wang's review point stands. The surviving ideas tend to be combined, not boutique one-error patches. Future decisive tests are already on the calendar of ambition: more lensed quasars, tighten time delay cosmography until it can referee Cepheids. Wider Euclid coverage multiplies early quasars until C models break or bend. Deeper Webb calibrations decide whether Friedman's intermediate camp or Ries's high camp owns the local sky. Next-generation CMB experiments remeasure Planck's peaks with different systematics. EC and successors watch whether dark energy's equation of state truly evolves. ARC test is a different knife. The tension will bleed under one of them, either as a measurement error or as a discovery. Stand inside Planck's map for a moment. The whole sky is a single photograph of a 380,000-year-old plasma, cooled into microwaves, speckled with acoustic peaks at parts in 100,000. That photograph is why cosmologists trust the early universe. Stand inside Eschew's galaxy for the other moment. A Cepheid pulsing while a calibrated supernova once flared in a system far enough into the Hubble flow that peculiar motions no longer dominate. Two excellent photographs, no intolerable mismatch. Return once more to Liffin's plates at Harvard. Woman paid as a computer found the relation that let the universe grow larger than the Milky Way. Every modern fight over 73 versus 67 still climbs her ladder. The Hubble tension is what happens when an inheritance becomes precise enough to notice its own contradiction. Precision is a gift that arrives with invoices, and if you want the tension in one image, hold two clocks. One wound by Cepheids and supernovas, one wound by sound waves frozen into the microwave sky. They disagree by about a toe on Kirchner's foot. After a century of learning how many feet we have, that toe is where new physics may be hiding. Friedman's caution also stands. New evidence can support the standard model in one analysis, while another analysis deepens the crisis. Science is not a press conference. It is a contested measurement. The public story should hold both facts. The tension is historically severe, and the local community is not unanimous on every decimal. Honesty strengthens the mystery rather than watering it down. 7 sigma disagreement between major pipelines is enormous, even if a parallel team finds a Milder gap. What would count as a resolution? A demonstrated systematic that shifts local distances by the required amount, confirmed across independent candles, or a new early universe component that fits CMB and structure while raising the predicted Hubble constant, or a late-time modification that survives distance duality and growth constraints, or a deeper revision of gravity that earns every other success Lambda CDM already owns until one of those arrives. The honest sentence is the one the opening already spoke. The two most accurate measurements disagree so strongly they cannot both be right within the model we trusted, cannot both be right within the model. That phrase, matter, nature is consistent. Our description may not be. The Hubble tension is the place where precision cosmology heard its own contradiction at high volume. Webb and Euclid did not mute it. They added early universe monsters that make an incomplete timeline harder to ignore. Rees wants the foundations re-examined. Mera says cosmology may be broken if the error is not observational. Schroy sees the start of a new model. Bira calls it the dream of finding something deeply wrong, so something deeply new can appear. Friedman reminds the field that the standard model still has defenses and that 1,000 papers have failed to produce an easy patch. All of those voices can be true at once in a living debate. Sandage spent decades defending a low expansion rate near 50, while others fought for 100. That second Hubble war was not pedantry. It decided whether the universe was old enough for stars and geology to make sense together. The key project's convergence near 70 felt like peace. Acceleration in 1998 then rewrote the ending without reopening the distance books completely, until Planck's precision and Schu's precision arrived in the same decade and refused to shake hands. And you hear 67 versus 73, translated into a human scale. At the distance of a rich galaxy cluster tens of megaparsecs away, those two rates disagree by hundreds of kilometers per second, enough that careful spectroscopy notices at cosmological distances the disagreement compounds through every integral over expansion history, gay, angular scales, growth rates, and inferred dark energy behavior all shift. Toe on Kirchner's foot moves the whole skeleton. The CMB is not only temperature. Polarization patterns record how light scattered off electrons at last scattering, and how it later traveled through large-scale structure. Planck's polarization and lensing measurements tightened lambda CDM further. That is another reason the early prediction is hard to dismiss as a fluke of one temperature map. Multiple channels inside the same satellite keep voting for the same low Hubble constant under the standard model. Baryon acoustic oscillations can be felt as a preferred separation between galaxies, about the scale the sound horizon had grown to by recombination, stretched by later expansion into a ruler hundreds of millions of light-years across today. Survey teams measure that bump in the correlation function the way you might measure the preferred spacing of houses built from the same blueprint. If early dark energy shrank the blueprint, the houses sit closer in physical units, and the whole late distance ladder inferred from bio shifts. That is why EDE is not a vibe. It is a surgery on a ruler. Gravitational lensing time delays have a beautiful cruelty. They care about absolute distances, not just distance ratios. Day of delay between quasar images is a laboratory clock tied to cosmology. As samples grow from a handful of lenses to dozens, the statistical power starts to rival Cepheid campaigns. That is why Troy and collaborators speak of a possible new model with the confidence of people whose method does not share Cepheid dust. Independent methods agreeing on a high number are how tensions become crises. Imagine teaching a classroom the age of the universe as 13.8 billion years and then admitting the local stretch rate wants a different calendar. Students ask which number to memorize. The honest answer is that age is an integral, not a sticker. Change early dark energy, change late dark energy, change the matter density, and the same local H0 can pair with different ages. Headlines that shave a neat billion years off the cosmos are usually oversimplifying the integral. The real story is messier and more interesting. The word crisis sounds like panic. In precision cosmology, it often means something colder, a discrepancy large enough that ignoring it would be malpractice. Rees's call to re-examine foundations is not theater. Amara's warning that cosmology may be broken is not clickbait when spoken from Keck. Friedman's defense of the standard model is not denial when her pipeline lands closer to Planck. Crisis here means the field must keep waking up early until one of those statements wins with evidence. You can feel the absurd scale another way. The sound horizon was laid down when the universe was a hot fog younger than many mountain ranges are old. 380,000 years. The Cepheid Schu's watchers may be tens of millions of years old as stars, living in galaxies billions of years old, calibrated by parallaxes measured from a planet 4.5 billion years old. The argument connecting those clocks spans almost the entire history of known time. Of course, a 9% crack in that argument feels like the ground moving. And yet the ground has moved before. Static universe to expanding universe, matter-dominated deceleration to dark energy acceleration. Arc timed the map gained a new street. The Hubble tension may be the next street. Early dark energy, evolving dark energy, interacting dark sectors, or something not yet named. Or it may be the last percent of dust and calibration humility. The telescopes are warm. The papers are fighting. The discovery, if it is a discovery, is happening in public. Step back to the century-long arc. Leavitt gave us candles, Hubble gave us expansion with a wrong speed. Bardet and Sandage corrected the latter. Friedman's key project narrowed the second war of 50 versus 100. Rees and others found acceleration and built lambda. Planck predicted today's expansion from the infant sky. Local teams measured a faster stretch. The disagreement hardened. New telescopes were supposed to end the argument. They turned it into the central drama of modern cosmology. Slipher gave us fleeing nebulae. Einstein, Friedman, de Sitter, and Lemaitre gave expanding geometries while Einstein still hoped for stillness. Shapley's universe died in a letter. The second war of 50 versus 100 taught the field that factor of 2 arguments are childhood and percent level arguments are adulthood. Percent level is where cosmology now lives. At that precision, a 9% gap is a chasm, and chasms are where discoveries hide. That drama is the calculation error named in the title, not a clerical mistake in one paper, but a mismatch between what the Big Bang's afterglow implies under lambda CDM and what the living universe shows on its distance ladder. If the latter is right, the Big Bang model as currently closed is incomplete. If the early prediction is right, something still biases the local universe at the percent level after every obvious contaminant was hunted. Percent level is where cosmology now lives. At that precision, a 9% gap is a chasm. Mount Wilson's 100-inch telescope, the instrument that let Hubble find Cepheids in Andromeda, was once the largest eye on Earth. Today, Webb and Euclid are larger eyes with different jobs, infrared depth and wide-field mapping. Yet they argue with the same constant. Hubble named that continuity is uncanny. Century of bigger mirrors has not erased the question of the stretch rate. It has sharpened it until the disagreement can no longer be blamed on bluer. Casatano's line about a 10% smaller prediction is worth sitting with. N% is a tip at a restaurant. N% is also the difference between a model that fits and a model that fails a discovery threshold test. Cosmology spent the 2000s celebrating percent-level triumphs. The Hubble tension is what percent-level science looks like when 2 triumphs collide. So, the calculation error of the Big Bang is not a typo in a textbook margin. It is the living mismatch between an infant sky prediction and a local sky measurement. A mismatch deep enough that ancient galaxies and early black holes now read like supporting witnesses rather than separate scandals. Whether those witnesses share one cause remains unknown. That they entered the courtroom in the same decade as a 7 Sigma Hubble clash is why this moment feels historic, and so the final question returns with more weight than it had in the opening. What if the universe is not expanding the way our best theory predicts? What if the problem is not our telescope, but the model we have trusted for decades? The instruments keep getting better, the gap remains. Ancient galaxies and early black holes tighten the timeline. Early dark energy and its rivals offer incomplete maps of a possible escape. No consensus yet. That is not failure. That is the sound of a discovery before it has a name. If you came for a neat verdict, the universe refuses to give one yet. What it gives instead is a sharper question than cosmology had in decades. Is space stretching faster than our best early universe story allows? And if so, what invisible chapter did we skip between the fog of recombination and the galaxies we measure tonight? Because if the Hubble tension is real, the biggest discovery in cosmology is not a museum piece from 1929 or 1998. It is the crack opening now, in the rate of space itself, while the telescopes are still warm and the papers are still fighting. Thank you for watching.